Hello and welcome to Problem Set 13. We will be covering problems from the topic An Introduction to Acids and Bases, pH, and Buffers today. If you have not already done so, I do highly recommend that you print out the worksheet that I'll be covering today. It is available online through my website. And with that said, let's get started. Number 1. Classify the following as a salt, an acid, or a base. So I'm going to go ahead and copy down number 1, A through E. A is sodium chloride, B is barium sulfate, C is hydrochloric acid, D is sulfuric acid, and E is calcium hydroxide. So A, you probably already recognize as a salt. It's such a common salt that we simply just call it salt instead of its proper chemical name, sodium chloride. So I'll go ahead and write salt here. But in case you didn't recognize that as a salt, just a quick reminder that a salt is formed in a neutralization reaction between an acid and a base. And the salt will have the cation from the metal hydroxide base and the anion from the acid. So in this case, sodium chloride, this is a salt that forms from sodium hydroxide neutralizing with hydrochloric acid. Barium sulfate, also a salt. This is the salt that will form from the base barium hydroxide neutralizing with the acid sulfuric acid. The cation from the base, barium, and the anion from the acid, sulfate. C, hydrochloric acid. It's in the name for you. This definitely has an acidic hydrogen. Hydrochloric acid is an acid. In fact, it is a strong acid. Sulfuric acid, also in the name, has two acidic hydrogens. And so we're going to go ahead and write here, acid. Calcium hydroxide. Remember that your group 1A and group 2A metal hydroxides are strong bases. Calcium hydroxide is definitely a base. It will produce lots of hydroxide anions in aqueous solution. Number 2. Classify the following acids as strong or weak. Okay, there's an A, B, C, and a D. And I'm going to go ahead and copy them down again. Hydrochloric acid, hydrobromic acid, hydrofluoric acid, and acetic acid. So remember that there are 6 strong acids, and if you memorize those 6 strong acids, then by default you know all of the weak acids as well. They're just any acid that is not on that list. So we already know these are all acids. It's given in the problem. It already says the following are acids. We just need to say strong or weak. Let's go ahead and write down our 6 strong acids. That might help here. Hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, perchloric acid, and sulfuric acid. Did I get them all? 1, 2, 3, 4, 6. Yeah. Okay, these are our 6 strong acids. So hydrochloric acid, definitely on that list of 6 strong acids. So let's write here, strong. That means that hydrochloric acid will 100% ionize to produce hydronium ion in solution. Hydrobromic acid, also on our list of strong acids. So let's write strong. Hydrofluoric acid is not on the list. Maybe you have to check twice there because you kind of expect it to be there since hydrochloric, hydrobromic, and hydroiodic are on there. But hydrofluoric acid is a weak acid, meaning that it will significantly less than 100% ionize in an aqueous solution and therefore produce small quantities of hydronium ions. Acetic acid, also not on the list, so therefore a weak acid. Okay, let's move on to number 3. Which of the following will conduct electricity when dissolved in water? So really, this problem is asking which is an electrolyte. So there's A through D. And I won't write them all out. I'll just write either electrolyte or non-electrolyte next to each of them. So remember that an electrolyte is a substance that will produce ions in solution and therefore is capable of conducting electricity. Remember that all acids and bases will produce ions in solution in an aqueous solution, and so therefore all acids and bases are classified as electrolytes. Any other substance that will produce ions in solution is also going to be classified as an electrolyte. So that would be all of your soluble salts, all of your soluble ionic compounds that will release cations and anions. What's not going to dissolve to release ions in solution are your molecular compounds that are neither acidic nor basic. They're going to stay covalently bound and not produce cations and anions. All right, so sulfuric acid. Acids are electrolytes. So I'm going to write electrolyte for A. It will produce ions in solution and it will conduct electricity. Sodium chloride. Sodium chloride is a soluble salt. It will produce cations and anions in solution and it will conduct electricity. So I'm going to write electrolyte for B. C, sodium hydroxide, a strong base, going to produce many cations and anions in solution and therefore conduct electricity. C is also an electrolyte. D, glucose, and the formula of glucose is given there in case you aren't familiar with it, C6H12O6. Glucose is a molecular compound that is neither acidic or basic. So glucose, when it dissolves in water, which it will be soluble in water, it can hydrogen bond and dissolve in water, it is not going to ionize at all. Those glucose molecules are going to stay intact, everything will stay covalently bound together, and therefore you will have no cations and anions produced when that glucose dissolves. So I'm going to write non-electrolyte. Okay, let's go ahead and erase here and go on to number 4. Okay, number 4, write a balanced equation to represent the reaction between hydrochloric acid and magnesium hydroxide. So hopefully you recognize hydrochloric acid as a binary acid because of the hydro prefix. That means hydrogen and just one other element which you can get from the stem chlor. So it's chlorine. And acids are aqueous, so I'm going to go ahead and write AQ there for the state. It's reacting with magnesium hydroxide, an ionic compound. So check the charge on the magnesium cation. It's a group 2 metal, so it's going to be a 2+ charge. It needs to lose 2 valence electrons. Hydroxide is a polyatomic ion, so hopefully you have memorized its formula is OH with a 1- charge. So it's going to take 2 hydroxides to balance out the charge on just 1 magnesium cation. So we're going to write that formula as MgOH in parentheses because there are 2 of them. And magnesium hydroxide is not soluble in water, so I'm going to go ahead and write the state here as solid. Let's erase this work to keep things nice and neat. So we're talking about an acid-base neutralization here. So we're going to combine the cation of the base, magnesium, with the anion from the acid, so chloride. Check your charges. Magnesium has a 2+ charge. Chloride has a 1- charge. So it's going to take 2 chlorides to balance out the charge on just 1 magnesium. That's why I wrote MgCl2. Magnesium chloride happens to be soluble in water, so I'm going to go ahead and write its state as aqueous. Let's erase that work there too. And our final product forms when the acidic hydrogen combines with the hydroxide of the base to form HOH, or in other words, to form H2O, water. And I'll write its state as liquid. We are not done yet because this reaction is not balanced. So let's draw a line down the middle and tally up what we have on each side. So on the reactant side, we have 1 plus 2 more for a total of 3 hydrogen. We have just 1 chlorine, 1 magnesium, and 2 oxygen. Okay, write them in the same order on the product side, just for good note keeping. So for hydrogen, on the product side, we have 2 chlorine, 2 magnesium, 1, and oxygen, 1. Okay, so I would recommend that you start anywhere but with hydrogen. Hydrogen is present in 1, 2, 3 substances, which means that you're going to have to get 3 coefficients right to get it balanced. All the other ones are present in just 2 substances, so just 2 coefficients to get correct. So since magnesium is already balanced, let's just go ahead and start with the chlorine. I can see already that we can easily balance chlorine by just putting a coefficient 2 in front of the HCl. Now that's going to change our number of hydrogen as well to 2 plus these 2, total of 4, and updates our chlorine and balances it by making it also 2. All right, let's go over here and balance our oxygen. If we put a 2 in front of the H2O, we'll update our hydrogen to 2 times 2, or 4, and our oxygen to 2. And that balances all of the elements, and we are finished with number 4. So I'm going to go ahead and just erase all of this work here because we're going to need this equation in problem number 5. Okay, number 5. Stomach acid is about 0.1 molar hydrochloric acid. How many milliliters of stomach acid will completely react with an antacid that has 500 milligrams of magnesium hydroxide? Hint, use your equation from number 4 and round your final answer to 3 sig figs. Okay, so we are trying to do a stoichiometry problem here. We are trying to convert between quantity of this reactant here, magnesium hydroxide, and figure out what quantity of the other reactant is going to react. Okay, so clearly we're going to need to go through the mole ratio. Let's try that again. Okay. Number 5. Stomach acid is about 0.1 molar hydrochloric acid. How many milliliters of stomach acid will completely react with an antacid that has 500 milligrams of magnesium hydroxide? Hint, use your equation from number 4 and round your final answer to 3 sig figs. Okay, so we are trying to figure out how much hydrochloric acid is going to react with a given quantity of magnesium hydroxide. This is stoichiometry. Okay, so we clearly need to go through the mole ratio. Remember from way back in our stoichiometry tutorial that the mole ratio from a balanced chemical equation is the only way that you have to quantitatively relate two chemical substances in a balanced chemical equation. So we're going to need to convert between moles of magnesium hydroxide and moles of HCl. And in order to do that, we need to use the mole ratio. So I'm going to go ahead and label this mole ratio, which we can already see from our balanced chemical equation. It's going to be 2 moles of HCl to every 1 mole of magnesium hydroxide. But unfortunately, we don't yet know how many moles of magnesium hydroxide are reacting. We are given 500 milligrams as the quantity of magnesium hydroxide. But we do know, or I hope you know, how to convert between grams of a substance and moles of the same substance. We do that using the conversion factor called molar mass, and we can get that from a periodic table. So we can convert between grams of magnesium hydroxide and moles of magnesium hydroxide by looking up and using the molar mass of magnesium hydroxide. Okay, well, we actually weren't given grams of magnesium hydroxide either. We were given the quantity of magnesium hydroxide in milligrams. So we want to know how to convert between milligrams of magnesium hydroxide and grams of magnesium hydroxide. And that's just going back to the metric system. So I'm just going to write up here above the arrow. This requires us to remember our metric conversions. I'll write metric system. Milligrams to grams. Okay. Now we aren't actually asked for the quantity of hydrochloric acid in moles. We're asked how many milliliters of a 0.1 molar hydrochloric acid solution will react. So we need to add some steps on this side as well. We need to use the concentration, the molarity, to figure out the number of liters of hydrochloric acid solution that will react. So I'm going to write here, we're going to use the concentration. I'll just write cons, and in parentheses I'll write a capital M for molarity. That concentration is given in the problem. And then we're asked to finally express our answer in milliliters. So we're going to convert the liters into milliliters of HCl solution. And yet again, that is just using the metric system. Going from liters to milliliters, that is the good old metric system. Whew, so it's going to be a lot of work. It's a lot of steps in this problem, but it's all things that you do know how to do. It's just a matter of thinking through it beforehand and kind of mapping out what it is that you need to do. And that's why I like to write out my steps. And then I'm going to check them off as we go. All right, so let's go ahead and start setting up this problem. We have 500 milligrams of magnesium hydroxide. It's in a tablet form. How many grams is that? We know there are 1,000 milligrams in 1 gram. I'll go ahead and label that magnesium hydroxide. Okay. So milligrams will cancel, leaving us in grams. And I'm going to use the green pen to check off each step as we go. So we just did step number 1 here. I'm going to keep adding the steps and then pull my calculator out all the way at the end rather than stopping and calculating at each step. So I'm going to keep adding on here. Okay, so we've done step number 1. Now we need to find the molar mass of magnesium hydroxide so that we can convert grams of magnesium hydroxide into moles of magnesium hydroxide. Okay, so grams on the bottom, moles on the top. So what is this number here? Let's go to the periodic table. So grab a periodic table and look up magnesium. It is 24.31 grams per mole. For the 1 magnesium, but that's not it. There's also 2 moles of oxygen. So for the 2 moles of oxygen, it's going to be 2 times the 16.00 grams per mole. That's for the oxygen. And then for the hydrogen, it's going to be 2 times 1.01 grams per mole. Again, times by 2 because there are 2 of them in 1 mole of magnesium hydroxide formula units. All right, so add these up. And I'm going to do that with my calculator here. 24.31, 2.02. I get 58.33 grams per mole. So this is a number that I'm going to plug in right here for the molar mass. Okay, so now my grams of magnesium hydroxide cancel, and I now know how many moles of magnesium hydroxide are reacting. So that was this step right here. I just used the molar mass to convert between grams of magnesium hydroxide and moles of magnesium hydroxide. Not done yet. Now, I'm going to use my mole ratio to figure out how many moles of hydrochloric acid would react with this quantity of magnesium hydroxide. So I know there's a 1 to 2 mole ratio. For every 1 mole of magnesium hydroxide, two moles of HCl react. So my moles of magnesium hydroxide cancel. I now know how many moles of hydrochloric acid are required here. So I just did this step. I used the mole ratio from my balanced chemical equation to figure out how many moles of acid would react. I'm not done yet. Now I'm going to use my concentration in molarity to figure out how many liters of solution would contain that number of moles of hydrochloric acid. So I know that every 1 liter of that HCl solution contains 0.1 moles of HCl. I know that because I was given that information in the problem. It's a 0.1 molar hydrochloric acid solution. So I just did this step here. I figured out how many liters of my 0.1 molar solution would be required in this reaction to react with my 500 milligrams of magnesium hydroxide. I'm not done still because I don't want my final answer in liters. I want it in milliliters. So one last step. In every 1 liter of solution, there are 1,000 milliliters. All right, S-O-L-N, I'll squeak it in there. Liters cancel. My final answer will have units of milliliters. So now, put my equal sign here, I'm ready to type all of this into the calculator. But first, let me just check off that last step that I set up in the problem to convert between liters and milliliters. Okay, grabbing my calculator. So we've got the 500. Now I'm dividing by 1,000 here and I'm multiplying by 1,000 here. So that's gonna just be timesing by 1 overall. So I'm not actually gonna punch that into my calculator. I'm just gonna go straight to dividing by 58.33 and timesing the answer by 2 and dividing by the 0.1. And my final answer, you're told to keep 3 sig figs in the problem. So my final answer will be 171 milliliters. Let's write it right here. And that's of the hydrochloric acid solution. So 171 milliliters of that 0.1 molar hydrochloric acid solution can be neutralized if it fully reacts with our 500 milligrams of magnesium hydroxide. Okay, that was a lot of work. Let's go ahead and erase here and go on to number 6. Okay, number 6. Given the following information, classify the following as an acid or a base. Try to do these problems without using a calculator. So A, human sweat with a pH between 4.0 and 6.8. You probably don't even need a calculator for this one. You've already got the pH. And as long as you remember that a pH less than 7 is acidic, this problem should be pretty easy, and you should be able to classify A as being an acidic solution, weakly acidic, but an acidic solution. B, a vinegar solution with a hydronium ion concentration of 4.0, that's right, H3O plus, concentration of 4.0 times 10 to the negative 3 molar. Now this is the one that I really was hoping you wouldn't need your calculator for. I want you to be able to think through the hydronium ion concentration and how that relates to the pH without actually picking up your calculator and calculating the pH, which would be cheating in this problem. Okay, so we can see that the hydronium ion concentration is close to the hydronium ion concentration of a solution with a pH of 3, because with a pH equal to 3, we're going to have a hydronium ion concentration of 1 times 10 to the negative pH, so that would be negative 3 molar. Okay. But this solution is actually a little bit higher in hydronium ion concentration, which means that its pH is actually a little bit less. So this solution would have a pH somewhere between 2 and 3. And you should be able to deduce that without picking up a calculator. Okay. To just kind of reinforce that, let me go ahead and take these concentrations out of scientific notation. For some people out there, they really may need to see it that way to understand this. Okay. So I'm going to go ahead and write, I'm going to move my decimal 123.0040 molar hydronium ion concentration versus this one here, which is 0.001 molar hydronium ion concentration. So this solution is less than this solution, has a lower hydronium ion concentration. Okay. And then if we look at a pH of 2, that would be 0.01 molar. Okay, so 10 to the negative pH, so 10 to the negative 2, and I'm just taking it out of scientific notation. This would be less than the hydronium ion concentration of a pH 2 solution. So somewhere between a pH of 2 and 3. It lies somewhere in between. Okay, so because we know the pH is somewhere between 2 and 3, it's 2 point something, it should be easy to then classify that vinegar solution as an acidic solution. All right, C. A household cleaner with a pH of 12. A pH greater than 7 is basic, so we can quickly and easily classify C as a basic solution. All right, let's go on to number 7. A solution of 0.10 molar hydrobromic acid has a pH of 1. But a solution of 0.10 molar acetic acid has a pH of 2.88. Explain why the two solutions have the same concentration of molarity but a different pH. Okay, so let's write down here. We've got a 0.10 0.10 molar hydrobromic acid solution, and we're comparing that to same concentration, 0.10 molar acetic acid, so HC2H3O2 solution. So this one has a pH of 1, and this one has a pH of 2.88. Why the discrepancy? They have the same molar concentration, so why don't they have the same pH? Well, the simple answer is the hydrobromic acid is a strong acid and acetic acid is a weak acid. But let's dive in a little bit deeper than that. Okay, so let's go ahead and write that. This is a strong acid, and this is a weak acid. But let's really analyze what that means in terms of the hydronium ion concentration. Okay, so a strong acid is an acid that will give up its H plus easily and therefore 100% ionize in an aqueous solution. So when we write the reaction of hydrobromic acid and water to form bromide anions and hydronium cations, we should expect 100% product. No leftover covalently bound HBr. So in a solution, we'll just draw it in a little beaker here. We have bromide anions and hydronium cations. None of the reactants are floating around in there. There is no covalently bound HBr because it is a strong acid. 100% ionizes and converts to hydronium cations. So if we look at the mole ratio here, it's 1 to 1. So that means that for every 1 mole of HBr that reacts, we will get 1 mole of hydronium cations. So if we have a 0.10 molar solution, then it should be 100% converted into hydronium cations. So the concentration of the hydronium cations, and let's write that in a different color here, hopefully that'll stand out a little bit. The concentration of our hydronium cations will be the 0.10 molar concentration. What's going on here? Oh, last but not least, that means our pH will be equal to 1. Okay, so we can go ahead and type that into our calculator. Negative log of this number, you should come up with a pH of 1. What's going on over here with our weak acid? Well, we know that a weak acid does not give up an acidic hydrogen as readily, and therefore will be less than 100% ionized in an aqueous solution. So if we write that reaction between acetic acid, HC2H3O2, and water, H2O, to give acetate anions and hydronium cations, we should put a big arrow back, because in that beaker, we're actually going to have mostly the products here. We're going to have mostly reactants here. We're going to have very little product floating around in that solution. So we've got covalently bound HC2H3O2, of course lots of water because water is a solvent, I'm not going to write that, and only a little, acetate anion and hydronium cation. We have mostly reactant. We have very little product. And remember that pH is a measure of the hydronium ion concentration in the solution. So if we have a 1-to-1 mole ratio here. We might expect for every 1 mole of this that reacts, we're going to get 1 mole of hydronium, but the whole mole is not going to react. In fact, equilibrium is going to favor the reverse reaction, the side with a weaker acid and weaker base. So we're not going to get all 0.1 moles converted into hydronium in this case. We're going to get significantly less than the 0.10 mole conversion. Okay, so for here, it's right, for the hydronium ion concentration, it's going to be significantly less than that 0.10 molar. And that's why you're going to get a pH that is greater than 1, or as given in the problem, a pH of 2.88. Okay, number 8. Rainfall is naturally acidic with a pH of about 5.60. Acid rain with a pH of 1.87 was recorded in Scotland in 1983. Calculate the hydronium ion concentration for natural rainfall and compare it with the hydronium ion concentration of the acid rain that fell in Scotland. So we have natural rain with a pH of 5.60, and we're comparing that to the acid rain that fell in Scotland with a pH of 1.87, and we want to compare the hydronium ion concentrations. So remember that pH is equal to the negative log of the hydronium ion concentration, and the hydronium ion concentration can therefore be found from the antilog taken to the negative pH, so 10 to the negative pH. So we are solving for the hydronium ion concentration given the pH. So this is the equation that we are going to be using to solve this problem. So let's go ahead and start with the natural rainfall first. The hydronium ion concentration will be equal to 10 to the negative pH, which is 5.60. So the hydronium ion concentration will be, I'm going to grab my calculator here. So if you're not familiar with using antilogs on your calculator, I'm going to write down the sequence of the buttons that I push. Now I am using a TI-83 once again, so your calculator may work differently if you have a different model. Okay, so we want to first push the second log so that we get the inverse log. You'll see above my log button there is a 10 to the x, that's the inverse log. So on the TI-83, I push second, and then I push log, and that gives me 10 to the, and my first bracket. And then I want to put in this number here for my exponent. So I'm going to push negative, and then my number, which is my 5.60, and then I'm going to close the bracket. It gave me the first bracket, but I have to close the bracket when I'm done putting in my number. So negative 5.6, close my bracket, and press enter. Okay. All right, and my answer is, for the hydronium ion concentration, 2.5 times 10 to the negative 6. And don't forget your unit for the hydronium ion concentration in these problems. It's always molarity. So molar. Okay, let's do the same thing over here for acid rain. So the hydronium ion concentration will be equal to 10 to the negative pH, so negative 1.87. So I'm going to punch that into my calculator again. So I'm doing the anti-log, so I'm going to push second log to get to my anti-log, and then negative pH, so negative 1.87, close my bracket and press enter, and I get a hydronium ion concentration of 1.3 times 10 to the negative 2. Don't forget your unit, it's molar. Okay. All right, so you can kind of ballpark these answers to make sure that what you came up with is correct. Make sure you didn't punch in something incorrectly. So we had 10 to the negative 5.6, so that should be close to 10 to the negative 6, and it is. And then over here we had 10 to the negative 1.87, so that should be close to 10 to the negative 2, and it is. Won't be exactly 10 to the negative 2 because it's not exactly 1 times 10 to the negative 2. It's not exactly a pH of 2, excuse me, so it won't be exactly 1 times 10 to the negative 2, but it will be close. You can kind of ballpark it. Okay, let's go on to number 9. Okay, number 9. Which of the following could be used to make a buffer? We've got A, nitric acid. I'm going to go ahead and write the formula here, HNO3, and sodium nitrate. So sodium is 1 plus, nitrate is 1 minus, so I'm going to write a 1-to-1 ratio there. B, hydrochloric acid, HCl, and sodium chloride, NaCl, again, 1-to-1 ratio for the 1 plus and the 1 minus charge. C, sodium dihydrogen phosphate, so NaH2PO4, and potassium hydrogen phosphate. Okay, so I'm going to really quickly just write out the dihydrogen phosphate anion, which has a formula H2PO4 1 minus, and the hydrogen phosphate anion, which is HPO4 2 minus. I'm going to write those out because we haven't really used those very much throughout the tutorials. So you can see that it takes 1 sodium cation in the sodium dihydrogen phosphate, but it would take 2 potassium cations in the potassium hydrogen phosphate because the hydrogen phosphate has a 2 minus charge. So 2 potassiums, each with a 1 plus charge. And D, acetic acid, which is HC2H3O2, and sodium hydroxide. Okay. All right. So first thing that we should probably do here is talk about what a buffer is. So remember that a buffer solution is capable of resisting changes in pH, and it works through the presence of a weak acid and its conjugate base. I'm going to write that down. So we need a weak acid and its conjugate base. Okay. So right away, we can go ahead and eliminate any one of these that has a strong acid. A strong acid will not function as a buffer because it will 100% ionize, and therefore you won't have a conjugate acid-base pair in that solution. Okay, so let's eliminate A. Nitric acid is a strong acid, and we should eliminate B. Hydrochloric acid is a strong acid. So A and B cannot make a buffer. I'm going to write over here, strong acid. Strong acid. You can't have a conjugate acid-base pair. All right, so let's look at C in a little more detail. So sodium dihydrogen phosphate and potassium hydrogen phosphate are both soluble salts. You can look up their solubility and convince yourself of that if you need to. So they will dissolve in an aqueous solution to release the cations, in this case sodium, and the anions, the dihydrogen phosphate, in this case the dihydrogen phosphate anions. Same thing here. It's a soluble salt. So we will get potassium cations and hydrogen phosphate anions. We're actually going to get 2 potassium cations for every 1 formula unit of this that dissolves. So I'll go ahead and put a 2 there so you're not wondering where did that potassium go. All right, so let's draw our beaker and really look at what would be floating around in a solution prepared with these 2 salts. So we would have sodium cations, dihydrogen phosphate anions, potassium cations, I'll go ahead and indicate the 2 there, and hydrogen phosphate anions, all floating around in that solution. So take a minute and look at that. Do you see a conjugate acid-base pair? Remember that a conjugate acid-base pair are going to be off by 1 H+. The acid is going to have an extra H+, the base will have 1 fewer H+. So hopefully you were able to identify the dihydrogen phosphate anion and the hydrogen phosphate anion as a conjugate acid-base pair. They are off by the presence of 1 acidic hydrogen. So any added base will be consumed by the conjugate acid, which is the dihydrogen phosphate anion, and any added acid will be consumed by the conjugate base, which is the hydrogen phosphate anion. So this will function as a buffer. Not only will this function as a buffer in the right proportions and with the right preparation, but this is actually one of the main buffer systems at play in bodily fluids. The dihydrogen phosphate, hydrogen phosphate buffering system. All right, let's take a look at D just to finish this one off. Okay, we have a weak acid, but look here what we have. We have a strong base. It's not going to be the conjugate base of the weak acid, and therefore the acid and the base will consume each other. We need a weak acid and its conjugate base so that they can be present in that equilibrium and not consume one another. They can be present in the same solution and not consume one another. So in the case of D, let's go ahead and circle C because we just said it's the answer. This is a buffer solution. In the case of D, label that C, label this one D. Let's go ahead and write the neutralization reaction that you're going to get when you mix that weak acid and that strong base. Okay, we're going to get acetic acid and sodium hydroxide reacting in a neutralization reaction to create just a salt and water, cation of the base, anion of the acid, gives us sodium acetate for our salt, and the acidic hydrogen combining with the hydroxide anion will give us HOH, or in other words, H2O, water. Okay. All right, so D is not going to be a buffer solution. That acid and base will neutralize one another. All right, so let's go ahead and erase here and go on to number 10. Okay, number 10. An ammonia solution has a hydronium ion concentration of 2.3 times 10 to the negative 12 molar. Calculate the pH of this solution. So we are given the hydronium ion concentration. It's 2.3 2.3 times 10 to the negative 12 molar. And we want to find the pH. So pH equals negative log of the hydronium ion concentration. So we just need to plug in our hydronium ion concentration here. We get pH equals negative log of the 2.3 times 10 to the negative 12 molar hydronium ion concentration. Okay, so if you are not familiar with using logarithms on your calculator, I am going to show you the sequence of button pushing that I do here on my TI-83. And again, if you have a different calculator, the sequence may be different. Okay, so first thing you're going to do is press the negative and the log button. And that's going to give you your first bracket, so you don't have to put that bracket in. And then you're going to type in the number. So 2.3 exponent negative 12. And then you're going to close your bracket. So tell it when you're done with that number. And then you're going to press enter. Okay. And I get for my pH 11.6. The pH of this solution is 11.6. Now, if you have a more simplistic calculator, then it's very likely that you'll need to punch this in the reverse order. So you'll put in your number, so that would be the 2.3 times 10 to the negative 12. Then you'll hit log, and then you'll hit the negative. Okay, so if you're doing it this way and it's not working and you're not getting the right answer or you're getting an error or something, try the reverse order and see if that works on your calculator. If that fails, you probably need to go and find your manual. Okay, so that will conclude our tutorial, or our problem set rather, number 13. I hope that you will consider tuning in to tutorial number 14. Thank you.